Good afternoon, everyone, and welcome to the 2020 Fluid Power Technology Conference virtual series. My name is Mike Ferentz. I am the publisher of Fluid Power World Magazine. And I'd like to thank you all for attending this, our 8th installment in the Fluid Power Tech Conference virtual series. First, as always, I'd like to go over a few housekeeping details regarding Hopin, our platform today. Over on the left side of your screen, you'll see a 4-button navigation panel. The home button is the best place to go to see which of the 4 areas is live. The stage is where the keynote will occur. The Q&A button will take you to the Q&A session, and the 4th button is for our showcase, which features videos from all of our sponsors. Please visit that area for more information about our sponsors. Now, if you look on the right side of your screen, you should see a white area that is used for the chat function. If you don't see it, chances are you have it minimized, and you can use the small caret icon to maximize that area and bring the chat function up. If at any time you're having a technical or navigational problem, please just let us know right through that chat feature. You can also ask questions in the chat feature that we will ask at the Q&A session at the end. While you're watching the keynote session, you will be in listen-only mode. But once we're in the Q&A session, the first 20 people who sign in can turn on their webcam and microphone, which is our preference, and participate with questions in the discussion. You can also just listen in the Q&A session if you would prefer. I'd like to take this opportunity to thank our sponsor and presenter today, FD Groups America. FD Groups America is the North American branch of the French parent company Fluid Design Group, which offers innovative, reliable, robust solutions for hydraulic and electronic technologies. All Fluid Design Group's developments are focused on the user's requirements. Therefore, their components and systems are specifically designed for each customer. Fluid Design Group is composed of 5 complementary activity sectors. Fluid System specializes in the design and manufacture of hydraulic components. Cerebrum Engineering performs the R&D and computer simulation modeling. FD Integrator is dedicated to electronic controllers, embedded control systems, and programming. FD Groups America is the U.S. subsidiary to expand business toward America, and FD Groups China is the Chinese subsidiary to export business to Asia. Their goal is to export the know-how, the strict standards, and quality of their products that have made their strengths in France. The common factor between the 5 activity sectors is quality, trust, and responsiveness. For more information, please contact Celine Cabana or visit their website at www.fd-groups-america.com. Please support FD Groups and all of our series sponsors, which are helping to bring you this great content. If you will be tweeting about today's event, please use our hashtag FPTC2020. Now I'd like to tell you a little bit about today's speaker. Ashley Busquets Wondergem is a simulation engineer with FD Groups America, specializing in model-based design. She attended Saginaw Valley State University in Saginaw, Michigan, for her BSME, graduating in August of 2012. While enrolled at SVSU, she was employed as an undergraduate co-op engineer at Dow Chemical Company in Midland, Michigan, from May 2010 to July 2012, with a fluid mixing group. In August of 2012, Ashley began her graduate research at the Maha Fluid Power Research Center at Purdue University under the supervision of Monica Avanti-Sinova. Her research focused on microsurface shaping, of the piston-cylinder interface of an axial piston machine, utilizing an advanced modeling tool. After she received her MSME in December of 2014, she transferred to the Department of Agriculture and Biological Engineering with a fluid power specialization, receiving her PhD in February of 2018. And with that, I have the honor of turning over today's session to Ashley.
Thank you for the kind introduction, and I want to welcome everybody to my talk today. Let me just bring up my slides. So today I will be talking about processor in the loop. This is a method that's a powerful simulation tool for optimal control systems. As Mike discussed a little bit, our parent company is the Fluid Design Group in France. This includes Cerevom Engineering, which is the engineering and multi-physics simulation, Fluid System, which is focusing on systems and components for fluids, FDE, which is the electronic components and ECU, and then under these groups are also the FD groups America and in China, bringing the expertise of the entire group into these regions. FD Groups America specializes in multi-physics model-based design workflows. We specialize in design with simulation, and this includes testing to feed the model, to validate the models that we create. We work closely with any collaborators that we have to meet the requirements that are necessary to the projects. Also included in the part of the simulation, which I will speak more about today, is the control and software aspect. And then finally, like I said, working with our collaborators, reporting in the end to give the best outcome of a project possible. We work with 1D multi-physics systems modeling, but we also include 3D systems as well. This includes the FEM in the multi-body structural analysis. And we can also do some co-simulation between the 1D and 3D to really have a very precise model. Included in these models, we can consider the CFD when it comes to aerodynamics, hydraulics, even thermal. And again, what I will focus on today, the control systems. So designing and tuning supported by model in the loop, software in the loop, and processor in the loop. And also reverse engineering, so component characterization in order to feed our models such that we have a well-working model. And also there's a part that we can do tools and specific applications development for various companies that need something more specific. Our process, like I said, this model-based design, we start with 1D multi-physics modeling to create a global virtual machine. We can feed this model with 3D dynamics, so considering the flexible body, or also the thermal flow CFD, as well as I said, the reverse engineering. And once we have this complete dynamic system, we can focus on a structural analysis. And so from this dynamic system, we can deduce the forces on the parts, feed this into a FEM analysis on each component, understand the stresses on each part, and get a durability lifetime of the part using the SN curves. But again, what I will focus on today is the pill method. So we can control the model virtually, but through a physical controller. This way we can predict any unsafe conditions in which we're able to prevent these in the field then, and also reduce the tuning time to the HIL method. We cover all systems. So when I say multi-physics modeling, I'm speaking of a complete model. We can include the electromechanics, the energy, internal combustion engines, any thermal considerations, mechanics, hydraulics and pneumatics, and then, like I said, focusing today on this control. Just a few definitions as I go forward to make sure we're all on the same page. The model in the loop, the MIL method, is a technique used to extract and define the control logic based on the behavior of a system or subsystem in a way that the model can be used to test, simulate, and verify that model. So this is the first level of validation for any algorithm. And from here, we decide on the choice of controls. At this point, the model is very precise when it comes to the dynamics, including everything possible. But it's a long calculation time, and the control system and code is not is high as high of a level as it will be later on. The SIL method, which is the software in the loop, is a technique used to evaluate the executable control code on the digital twin. So here, this is the second level of validation of the control system and code, but this is at this point without the actual controller in the loop. Still, we have very high dynamics and precision, a longer calculation time, but we're working more toward a higher level control system. From there, we go to the PIL asynchronous, which is a real-time model. This is a technique used to evaluate the processor with the executable code on a simplified digital twin in real time. So this is a third level of validation. And at this point, we actually connect a physical controller, but it's on a simplified model such that we can reach that real-time communication. So the real-time model is quite a bit simplified. So the dynamics and the precision are not as high, but we have a much faster calculation time and still a good level of the control system at this point. And then finally, the PIL synchronous. So this is the processor and the loop synchronous. It's a technique used to evaluate the processor with the executable code on the complete digital twin. This is the fourth level of validation of the control system and the code. So again, you're still using the physical controller in the loop, but you're using it on a more complete model. So you have a good level of dynamics and precision, somewhere in between on the calculation time with that balance, but you're at the highest level of testing the control system here to really make sure that it's going to work. At this point, I want to mention a little bit too, sometimes we may use a little different terms in order of PIL and HIL. So after this, the HIL comes into play. We call this the hardware in the loop. That's where we actually connect this physical controller that we're testing on the digital twin to the actual hardware, whether that be the machine, the tractor, anything like this, and test it at that point. At this point, the controller should work very well. The only difference is that they will need some fine tuning in order for the feel of the operator, which we'll never be able to get in the digital twin. Just a little more on the asynchronous versus synchronous methods. So the asynchronous PIL is a faster iterating process because it's a real-time model, but because in order to get that speed to communicate with the controller, we need to approximate the behavior and the dynamic simplification. So you can see here on the figure, they're speaking back and forth between the controller and the model as fast as they're providing the information to one another. When it comes to the synchronous PIL, it's a slower iterating process between the controller and the model, but we have a more reliable behavior and complete dynamic resolution of the model. So you can see here, they pass information back and forth one at a time as it's calculated on each. Again, takes a little longer, but we need to find this balance then between the reliability of the model and the speed. We mainly use AMASIM as a user library. Specifically at Cerebrum, they've developed a customized library in AMASIM to be able to receive and send CAN frames via a simple USB adapter. Also in this model, it integrates in this library, it integrates a protocol that allows the synchronization between the model and the processor. So there's something additionally added there that they know they have to wait for each other to communicate. Like I said, this is something specific to our company because we use this synchronous PIL method very often in many of our projects. And when it comes to the benefits of using the PIL method, it's mostly about optimizing the tune time. So you can test, improve, and debug the controller before it's ever on a machine. It's solely on the digital twin. So we can, as a consequence, cost efficiency. This is reducing the time to optimize and to get that final to market. Also security, you minimize not only the risk to the operators here during tuning time, but also um, the risk to the machine itself. So you can test it at very extreme conditions, and also reliability. So when it comes to the synchronous PIL method, you can minimize any simplifications on the model such that you can still get a good test of your controller. So just a general workflow to really understand better how I'm talking about we go about this here. You start with a digital twin. You can feed this digital twin with CFD analysis, structural analysis, and reverse engineering so that we have the highest level of this digital twin. From there, we can test the component sizing, failure prevention, and design optimization. So we really make sure that whether it's trying to optimize the machine, whether it's starting from scratch or using a machine that's just having some difficulties that we're trying to find. We really make sure that we have the best model and the best design because you have to have that first before you start with the controller. So from there, we simplify this digital twin when possible. It's not always possible to be able to test the controller, but with this reduced model, we can test it back to this complete digital twin so that we can verify the accuracy to be to be sure that what we're testing is worth anything. From there, we can connect the controller and do this PIL asynchronous um, method on the simplified digital twin to just simply test the control laws, make sure they're defined correctly, everything's working with connecting the controller. And then from there, we can really test it in the PIL synchronous model, again, validating these control laws. So just a brief story, how we even got into this in the first place. Back in 2014, there was a manufacturer of heavy equipment. They came to us asking us to size some actuators and develop the control software for their machine. We modeled their machine using SimCenter Amazon, so we could correctly define these control laws and have confidence in this. Just to get an idea of the machine, 7 meters high, 11 meters long, 5 meters wide, very large machine. At 38.5 tons, that's empty. So even then you can have a larger weight, 8 independent wheels and 8 height adjustable suspension. So a pretty complex machine as well. So saying that, we spent some time then after some months to debug and adjust the control software once the prototype was finally ready. So no PIL method at this point, only directly to this HIL, connecting the controller on the machine. So we realized we really need to introduce this PIL method, implement this, and keep this a standard so that we can save this time later on down the road for our customers. So I'm going to get into some examples of some cases that we've done since. So the first one I'm going to talk about is an entire train employed to replace the catenary consoles. You can see the video along here showing what I'm talking about. The objective of this project was to develop the control software to be able to stop the moving components from going outside the defined intervention zones. Very important when it comes to safety here. As you can see in the video there, you have 2 tracks. So you don't want this bucket to be able to move into the other lane of an oncoming train and risk any harm to the operator as well as the equipment itself as they're doing this work. To get a better idea of what I'm talking about here, the train is composed by 2 trolleys moving on wagons, having 2 of these platforms each. One wagon has 4 different cranes and 2 platforms. So then, exploiting the digital twin, the first part was to create this very complex model. We validate the actuator sizing, hydraulic motor and gear reducing sizing, the velocity of the movements, and also the stability of these movements. So from there, we could actually utilize this digital twin and find that they needed to replace some of the hydraulics on their system, such as the counterbalance valves, the proportional valves and actuators, and also optimize the structure kinematics so that there was more stability for the operators that were using this. From there, we could reduce the model then once we had the complete model. So we could actually, in this case, have a kinematics only model. This was adequate to give us the real-time interaction once it came to the PIL asynchronous. So for example, what I mean by this model reduction, we could take an actuator and replace it with a spring damper, or we could take a valve and just replace it with a simple flow characteristic table, and use this to get a little bit of a dumbed down version of the dynamics, but still able to test our controller on that. From there, I want to show some results. You can see here we have our dashboard in AMASIM in which we can control the motion of this platform connected through a simple USB for the CAN bus for the controller to the simplified digital twin model, which was in this case in asynchronous testing in real time. When I play here, you can see this live view of what we're getting from the model testing the controller here. Just a few points to watch as the video plays. The green means that the platform is in a safe zone. The yellow is a buffer zone, and the red zone is off limits. So you can see it kind of gets into that yellow zone before it stops at the red zone there. So the AMASIM model computes the component's position in real time in virtual sensors, and it sends this information to the controller. And from these signals, the controller will check if the platform is inside this intervention or the green zone. It'll start reducing the movement speed as it reaches the yellow buffer zone, and then it'll stop movement completely at the red zone as this is off limits due to the safety precautions that need to be taken. And then from there, we were able to actually implement it on the machine, show that it works with minor tuning. So you can see here, oh, sorry about the sound. So you can see here, yeah, it starts moving. He gets to a point outside of the safety zone. It'll slow down and stop. So the controller does exactly what it's expected to. Like I said, minus a few minor tuning points for the feel of the operator. Second case that I want to talk about is a Locotractor for the railroad maintenance train. And the objective here is to not only check the hydraulic transmission and component sizing, but then program the controller such that it manages traction control. So I think I have a picture here. It'll come up that it shows the grade of the land that this train is usually traveling. So it's very important that in different weather conditions, the train is not slipping and that it's able to smoothly transmission as it's going uphill, downhill, and maintain a constant speed. In other words, safe for the operator and also anyone around. It's about 4 meters high, 12 meters long, and 3 meters wide, and it's 52 tons. It can haul up to 6 wagons at 20 tons each. And the track slope, like I mentioned, is a 30 per mil grade. So a decent slope for a train of that weight. Then with the model, with the digital twin, once complete, we were able to validate the engine, the hydraulic pump, and the motors and gear reducers, and also the sensors that would be used for the controller. Very important with this one, with the energy consumption anticipation. For the train, we were able to take into account the drag force on the locomotive and the wagons, the rolling resistance, the consumption due to the cooling system, and the rail slope and curvature. So again, this is very important to be able to consider the real world in the model such that when you connect it to the actual train, it works as expected because these taken into consideration make a large difference. When it comes to the control laws, this model was very complex, so it wasn't possible to do a real-time model. It just wouldn't give us the information required. So utilizing this library that was created, we could do the synchronous model, just test directly the synchronous model. The control laws were defined and tested thanks to the model in the loop. And then, like I said, we could use the synchronous PIL method to validate them. Showing some results here, we had a dashboard set up in AMASIM, again, similar to the last one that I showed. And then the controller connected through a USB to the computer, directly speaking to this somewhat simplified digital twin. So again, from the controller, the goal was to change modes smoothly. So if you go from, like you can see on the dashboard here, the traction the holding, or the neutral, needed to have a smooth shift. So the computer then sends the engine rotary speed, the hydraulic motor and pump displacement, and also a braking force signal that you can command there. And then the Amazon model computes the physical values and sends the sensor signals back as those two talk. And we can see some plots here of the speed of the displacement of the engine, I'm sorry, displacement of the motors and pumps, just to really make sure that what we're getting makes sense and is really what they're seeing on the actual train. And then testing this on the hardware in the loop. Again, sorry, I don't know if you can hear the sound. Um, it's not so exciting, but the exciting part is that we could really just plug in the controller and it worked, except for a few minor adjustments due to the feel of the operator. The more interesting part maybe is to look at the plots then, comparing the real plots on the left for various different aspects that we're looking to the simulation plots on the right. And you can see we're matching quite well. The controller is working as expected once it's actually on the hardware. And then finally, one last case that I want to talk about here. We're actually in the process of working on this project for an autonomous vehicle. It's a tractor sprayer, and the goal of this project is to optimize the field use and yield. So we need to develop the control algorithms based on the available or implementable sensors to safely drive the tractor on an optimal path while avoiding obstacles. And by obstacles, I mean anything stationary in the field, whether that's a building or tree, but also if there's another tractor or a person unexpectedly running across the field, we need to have a safety protocol in order for that tractor to prevent an accident from occurring. So this is being tested on a tractor sprayer. It's tested on field terrain with surface information that we're able to import from the NASA data. We add then other visual elements just to test, which I was saying, like vegetation, trees, weeds, because that's an important one for the sprayer too. And then buildings or fences that are stationary in the field, as well as people and animals that may be a little more unexpected. And we need to be able to operate also in various weather conditions. So the important part here is that maybe it's raining or overcast, you're not getting as good of a visualization from some of your cameras. So we need to be able to take that in account under those situations to still maintain safe operation. So the exploitation of this model first was to validate the hydraulic components and the chassis stability. From there, the physical model of the vehicle needs to include the mechanics, so the chassis, the suspension, the wheels, the ground contact, such as this, but also the hydraulics, so the pumps, motors, valves, etc. And then the terrain, like I was talking, we were able to import this as a series of coordinate points from NASA so that we're really testing it on something physical, not just made up in a simulation world. We include sensors to visualize this data. This is fed to a plant model via FMU co-simulation, such that we can have a contact between the model, the sensors, as well as the controller. To get into a little more, the sensors that we're using for this, we can implement many different sensors, whatever's necessary for this specific autonomous driving case. Such as classic RGB, which you can see on the right, kind of what you and I would see to the eye. The depth, so the black and white one there, so you can kind of tell the distance of how far away things are, and the semantic segmentation, which so you can see the different colors according to the categories, however that's set. Radar, so a conical view, which detects elements with 2D coordinates and speed relative to the sensor. LiDAR, which is a laser remote sensing, so you can obtain the position, and then you can see that there on the right. And then the GNSS Global Navigation Satellite System, as well as we could implement an IMU, accelerated and accelerometer and gyroscope. And so the point is that there's several levels of modeling and settings possible for each sensor. And these sensors, for future view of what I'm going to show, are placed between the wheels at the front of the vehicle. So then getting into some results of this, we could validate this control implementation via the SIL method. And you can see here the tractor running along. You can see the views of the different cameras. In this case, we're using a depth camera, LiDAR, the segmentation semantics, and the RGB. And like I said, to speak, we're using this FMU between the model, the controller, and the visuals here. So from here, we could add to our controller. You can see on the left, without the correction, being in a vineyard, the sprayer on the hill is actually starting to veer off of the path of the line of the vineyard. So we can control this trajectory with LiDAR and maintain the tractor right in the middle of that line so that no damage is done to the crop. And you can see here then just in a different view how it maintains that the corrections for that the center of gravity. As far as object detection, you can see here again how we can use these different camera views to spot something and then add into the controls to allow to correct the sprayer from running into anything like that. And then another interesting one is weed detection. So with these sprayers, it's important to distinguish the crop from the weed when it comes to terms of crop projection. So we can isolate the green elements of the image and then label them as a weed area, whether it's maybe uncertain or it was initially detected, but it's deemed not of interest. You can see on the video here then just to get an idea of what this image would look like. And then we can implement this into the control system, like I said, to determine a weed from a crop in order to get the maximum crop production. So just to kind of go over everything in general, again, the benefits of this PIL method is cost efficiency. So in this case, the real machine is replaced by its digital twin. The control system is developed before there's any prototype manufacturing. This way we can really get a feel of what's happening before any money is spent on a prototype at all. And also, like I spoke about a little bit too, we can really optimize the system before trying to optimize with the controller, which is also very important. So at the time of the prototype, then we can deliver a ready-to-use control system. And then in the end, when it comes to HIL, the tuning time is reduced by 5 times. For security, the control verification is done from the office using the digital twin. So I don't pose the same risk sitting at a computer running these models as what it would to the operators in the field or even to the machine in the field. When testing at some very critical situations, I can push it a little further without having to worry about safety. I should say safety of myself while testing. And then reliability. So the control laws can be verified with a complete model. This means that 80% of the work is done before the tuning time. The remaining part is just the comfort adjustments of the operator, which, like I said, you cannot feel in a model, so that needs to be done at that point, but we can get up to 80% of the work done before it's even tested on the actual hardware. For that, I want to thank you for your attention. If you have any questions beyond this or are interested in anything, you can let Celine or myself know, as our contact information is there, or you can visit our website at the www.fd-groups-america.com. So thank you.
Okay, great. Thank you, Ashley, for that excellent presentation. FD Groups has been a regular presenter at our live in-person Fluid Power Technology Conference which we hope to resume in 2021, at the same time keeping our virtual series going. So this presentation, along with all of our presentations, will be hosted on the Fluid Power Tech Conference website in an on-demand version. You can take those in at any time. So for moving to the Q&A, and I invite you all to move to the Q&A session, simply click on the Home button, wait a few seconds, and then click on the Q&A session. And then you may need to refresh your browser at that point to join the Q&A. And I invite you to turn on your camera and your microphone and ask questions of Ashley. And we'll be joined there by Celine Cabana from FD Groups as well. So I will see you there.
Hi, everyone. Thanks for joining. It's Ryan from Fluid Power World. Just as a reminder, Ashley, I believe Celine, and then Michael will be over shortly. Hi, Celine.
Hi.
How are you?
Good, and you?
Good. So the people who are on the stage, Ashley and Mike, will be over shortly to answer, or just kind of go through the Q&A, and Celine is here to answer any questions about FD Groups. Please hang tight while they finish up things on the back end on the stage, and they will be over shortly. There we go. All right, Mike.
Thank you, Ryan. I am showing that we do have 12 people in the room. The 12 folks can certainly turn on their camera and microphone to ask questions at any time. You can also continue to use the chat function to enter a question at this point. I do have a couple of questions that I will start with that we have in the queue. The first question, oh, by the way, I introduced Celine in the stage session. Celine Cabana is with us now as well from FD Groups. Do you want to say anything, Celine?
No, welcome. Okay. Thank you for being there.
First question, how do you know that your model is precise?
Ashley?
Okay, so we have tested in the past. The way we started this simulation was mostly on customers coming to us that had problems with their machines. So we were able to recreate these problems in our model and then fix them from there. Now we have a lot of new customers that are wanting us to start something new from scratch. And in that point, we don't have anything to compare it to, but by following the same procedures that we've kind of become experts in the past projects, we know that these models are working well. In any case that we still have measurements, we can validate and really be sure of the precision of our models. Another thing to point out, though, too, is that our models are not necessarily about precision. If we're comparing two models, we don't need to be exactly matching the real world. We just need to know the benefits of one compared to the other, something like this. So they're as precise as we need them to be. We're sure of that. Celine wants to add anything.
Anything to add, Celine?
No, I think that for the summary, it's the experience that we have and the technique that we're using, validating and verifying our work along the way. So that summarizes it. Yes.
So once again, if anyone would like to ask a question, you can still use the chat function to enter your question, and I'll ask it of Ashley and Celine. Or welcome to join live. I'm showing that we still have 15 people now in the room. So we do have folks out there listening for answers, but I invite you to add your question. While we're waiting for that, I have another question. It's a two-part question. Which type of programming language are you using, and which type of controllers?
So the simple question is whatever our customer wants. We're able to work with really anything. We do most of our models on AMASIM using Simulink for our control software. And then for the controllers, using anything from Rexroth, IFM, anything such as this. Like I said, the simple answer is whatever our customers want, we're able to work with. We have quite a few experts in many different areas. So.
Okay, and Celine?
She answered. She answered. The thing is, we have worked with different type of controllers, Danfoss, Rexroth, AFM. We have done different type of programming also, and we can adapt really easily to any situation. Even for the simulation software, the simulation technique, we have it. So adapting to a tool is not a problem.
Okay.
Even creating the tool, like I briefly mentioned in our presentation, but we've done that for some customers as well. If they don't have access to certain programs, we can create the tool itself that they're able to use.
And Celine and Ashley are both reachable at any time. Visit the FD Group's website, ask their questions directly, and your phone number can be found on your website as well.
Yes.
So oftentimes people have questions, but don't have them formulated at the moment, but would be able to put them into words a little bit later on. So you'll be able to do that, to answer those questions, and you may generate some additional questions from the on-demand version of your presentation. So any other questions from our audience at this time? Otherwise, anything else you'd like to add, Celine or Ashley?
No, thank you for attending. Thank you for coming to our presentation.
Okay, very good. Well, thank you both very much for your excellent job today. And thank you for being a sponsor and presenter at the Fluid Power Technology Conference. And hope to see you again soon someday.
Yep.
Okay.
Thank you.
Thank you.
Bye.
That concludes our program for today.
Thank you.
Thank you.